My apologies that I can't be with you today. Didn't want to rob you of learning, so I thought I'd record a lesson real quick for you to be able to read through the lesson 1.5 and be able to work on some of the assignment anyway in my absence. So, lesson 1.5, we're learning about functions and logarithms, reviewing some things that you learned back in Algebra 2 and then touched again in pre-calculus. First of all, on page 37, it talks about the definition of a one-to-one function. One-to-one function is one on a domain if the f of a is not equal to the f of b whenever a does not equal b. Meaning, if I were to look at a function, like this one for instance, I'm saying that it's a one-to-one function if the output never gets repeated. Okay, never the same output in a one-to-one function. I plug in a value for x, it gives me an output, and that output never ever shows up again. One way to test for a function being a one-to-one function is to graph it and use the horizontal line test. Now, you might be familiar with the vertical line test to decide if something is a function or not. Well, the horizontal line test can help us determine if something is a one-to-one function or not. So to accomplish this, you graph the function and then imagine drawing a horizontal line, through the graph. If I draw a horizontal line through this graph, notice that it hits in not one but two places. What that means is that this particular output, whatever it may be, shows up twice. Therefore, this is not a one-to-one function right here. This being the V shape in blue that matches up with 2 times the absolute value of x right here. Second one, 1 divided by x squared plus 1 is graphed in red, and that graph is right here. Once again, if we were to draw a horizontal line, would I be able to hit in only one place at a time? I guess not. It's 1, 2 places. And the same thing would occur here and several other places. So again, not a one-to-one function. This final expression in black is the graph of 1 divided by x. If you notice, if I were to draw a horizontal line through here, hits in one place, one place, one place, one place, one place, one place, etc. And that will be the case for any portion of this particular graph. So I'm going to go ahead and say that yes, this is a one-to-one function. You get some practice identifying one-to-one functions. Again, I'd recommend graphing it and using the horizontal line test. Now, the next thing that you look at in this lesson is the idea of inverses. Inverse functions is something we've learned originally in Algebra 2, so I'm going to pull up a couple of old Algebra 2 slides to review how this works. So an inverse relation interchanges the input and the output values of the original relations, which means that we've got the domain and the range are interchanged. So for instance, if I have the original relation being these 5 points, 0, 6, 1, 4, 2, 2, 3, 0, and 4, negative 2. I'll go ahead and graph these once. So 0, 6, and 1, 4, and 2, 2, and 3, 0, and 4, negative 2. So there's the original relation. My inverse relation is the exact same numbers, but they're switched around. The x values, or inputs, become the y values, or the output. The y values, the output values in the first relation, become the input values of the second relation. So input and output are reversed, domain and range are reversed. This is now an inverse relation. Now, notice something. If I were to graph these 5 points, 6, 0 would be right here, 4, 1 is right here, 2, 2, 0, 3, and negative 2, 4. And if you remember from when we did this, these points are a reflection across the line y equals x. If I were to try to draw the line y equals x, it looks something like this. So through the origin with a slope of 1. All these points are reflections across that particular line. Instead of 0, 6, we've got 6, 0. Instead of 1, 4, 4, 1, 2, 2 stays itself because it's on that line. 3, 0 is 0, 3, 4, negative 2 is negative 2, 4, etc. So there's the graph of an inverse relation. Now, to find an inverse relation, we're switching the domain and the range. We're switching the inputs and the outputs. So simple way to put it, and again, this is slightly different than the way your textbook talks about it. The way that I believe is easiest to do it is to, when given a function or relation, you switch x and y, then solve for y. That's what I would do to find an inverse. For example, y equals 3x minus 1 is my original equation. If I'd like to find an inverse, I'll go ahead and switch the input and the output. So x is equal to 3y minus 1 instead. And then I'll solve for y, because I usually like to have functions written in terms of, here's the output based on the given input. So y being recognized as the output variable normally. Now as we solve, let's see, a couple of quick steps. We're going to add 1, and then we'll divide by 3, which I'm sure as calculus students is very obvious. Working slow here. So y equals x plus 1 divided by 3. If you wanted to write that as two fractions, that'd be okay. I like to leave them often as a bigger fraction like this, because then as I think about what happened to x in the original relation, plug in value for x, you multiply by 3 and then subtract 1. In the inverse, we do the opposite or inverse operations in reverse order. If subtracting 1 is the last thing to happen, then adding 1 is the first thing. Multiplying by 3 is the first thing, then dividing by 3 is going to be the last thing. So here would be an inverse relation. Now, another neat thing about inverses is that the two functions are inverses of each other, provided that when you compose them, taking the f of g of x and the g of f of x, you end up with the identity function, which is x. So if I were to try that out with these two, again, ignoring this one right here, if I were to call this f of x, and this I would then say is g of x. If I were to compose these two functions, I'm supposed to come up with the identity function x. So if I find the f of g of x, a little sloppy here with the mouse, please forgive me. That would mean I would plug function g into x and function f. So that would give me 3 times, parentheses, this function, x plus 1 divided by 3. Close the parentheses and then subtract 1 from that. Now, as I think you'll be able to see, if I multiply these together, 3 divided by 3 is going to cancel, turn into 1. I'll have x plus 1 times 1, which is x plus 1. And the 1 minus the 1 are like terms going to be put together. The final thing that I'm left with is going to be just x, the identity function. And I'll leave that to your imagination and trial to see if g of f of x also equals x. Now, a couple more inverses to practice on. If I want to find the inverse of a nonlinear function, the idea is the same. I switch x and y, I solve for y. So f of x is function notation instead of using x and y, but it's going to work the same way. I'll imagine that this is a y and this is the x, and we'll flip them. I'll say that x is equal to 4y to the fourth. And then I'll solve for y. Steps being to divide by 4. So I'll have x divided by 4 is equal to y to the fourth. And then to undo a power, I'd take a root. Or I could raise it to a rational exponent like 1/4, which is the same as taking the fourth root. So when I'm all done, instead of writing y, typically if it starts in function notation, you'll see this too. The f inverse of x. So a little -1 doesn't mean it's not an exponent, it's just, again, a symbol. This denotes that we're looking at the inverse of function f. And that inverse would be x over 4 to the 1/4 power, or if you want to write that as the fourth root of x over 4, that would also be acceptable. One more. When there's multiple x values, and these are the ones that seem to make students cry, unfortunately. Again, the process starts out the same way. I switch x and y and solve for y. So here we go. Cut this off. Switching x and y, we're going to have this. We're going to have x equals y plus 1 divided by y minus 4. Now again, the tricky thing here is that there's two variables that I need to solve for. So I'm going to do the best I can to get those variables, first of all, out of the denominator and then together on one side. In order to get those variables out of the denominator, I'm going to multiply both sides of this equation by the denominator, by that value 1 minus 4. Something on one side, do the same on the other. So here's what I have at the moment. I have x times, parentheses, y minus 4 is equal to, these cancel, so I'm left with just y plus 1 on the right side. So at least there's no more denominators, which is a good first start. The next step is I'm trying to get the y's to be together on the same side. So before I do that, I'm going to get rid of the parentheses by distributing x. So I turn it into xy minus 4x, and that equals y plus 1. Now, y here, y there. Let's get the y's together on one side or the other. So my next step is going to be to subtract the y from both sides, and I'll also add the 4x to both sides so I can move that around to the other side. So we're trying to get y's together on one side, everything else on the other. So here's what we got left. Xy minus y equals 4x plus 1. Now, when the variable for which I'm trying to solve is stuck in multiple terms, there may be some factoring that I need to do. So I want just one y here, so I'm going to go ahead and factor out that y. When I factor out a y from these two terms, I'm left with x minus 1. So now there's just one y in the problem, which is great because that was the goal in the first place, was to solve for y. So one last step, y times something equals 4x plus 1. Well, I should probably divide by that something, whatever it might be. So I divide this by x minus 1, and there we have our inverse. So f inverse of x is equal to 4x plus 1 divided by x minus 1. So there you have it, working with inverse functions, doing a couple different things with them. We'll do one more quick video, and that will be it for lesson 5.